All right, in this video, I'm gonna give an introduction to hypothesis testing. The objectives, hopefully, are to identify the null and alternate hypothesis in a hypothesis test, identify a right-tailed, left-tailed, and two-tailed test, use a test statistic to compute a p-value, determine the difference between type 1 and type 2 errors, identify the level of significance, understand the meaning and risk of rejecting or not rejecting the null hypothesis. Okay, so let's go ahead and give an overview here. So hypothesis testing is a statistical procedure that allows you to make inferences or draw conclusions about a population from a sample. The process involves a claim or hypothesis about a parameter of a population, often the population mean or proportion, and testing this hypothesis using sample data. Okay, so in hypothesis testing, we start with two competing hypotheses. The first one is called the null hypothesis. And is denoted as H sub 0, sometimes pronounced H naught, is the statement that is under investigation and commonly states the parameter is equal to a specific value. Usually the null hypothesis represents a statement of no effect, no difference, or things haven't changed. The other hypothesis is referred to as the alternate hypothesis. Denoted as H sub 1 or H sub A. It is a statement that the parameter differs from the value specified by the null hypothesis. The alternate hypothesis is a statement you adopt when the evidence, which is the data, is so strong that you reject the null hypothesis. There are three alternate hypotheses. We call a left-tail alternate hypothesis. It states that the parameter is less than a value specified by the null hypothesis. A right-tail alternate hypothesis states that the parameter is greater than the value specified by the null hypothesis. And a two-tail alternate hypothesis states that the parameter is not equal to the value specified by the null hypothesis. All right, so let's see how this works. We're going to formulate some alternate and null hypothesis. And so let's start with the first example here. Oops. Jumping around here. Boxes of a certain kind of cereal are labeled as containing 20 ounces. An inspector thinks the mean weight may be less than this. State the appropriate null and alternate hypothesis to test the inspector's claim. Okay, so the inspector thinks that the mean weight may be less than the advertised amount. So the null hypothesis is always going to take the value of equals. It's always going to have the equality symbol. And so this cereal is supposed to, on average, weigh 20 ounces. Or the mean, right? The mean. Okay, but the inspector thinks the mean weight may be less than this. So that's the alternate hypothesis. And that means the mean, according to the inspector, feels that it's less than 20 ounces. And so those are the two competing hypotheses. They come in pair. And usually it's a formulated from a claim. Okay, so the claim could be either be the inspector's claim, which it is in this case, or maybe the company that owns the cereal. Okay, so last year the mean monthly rent for an apartment in a certain city was $800. A real estate agent believes the mean rent is different this year. State the appropriate null and alternate hypothesis. So once again, they come in pairs here. And so the null hypothesis is that the mean is $800. The alternate hypothesis, since the real estate agent believes that the mean rent is different this year, means we're going to use the not equal symbol. And the reason for that is because the real estate didn't give any indication whether it was an increase or a decrease. So they just the world stage just believes that the mean rent is different from $800. Okay, let's continue on with the next example here. The Mars Candy Company states that the percentage of brown M&Ms is 13% for a full-size package of plain M&Ms. Suppose you bought a full-size package of M&Ms and found 15% of the package were brown M&Ms, which makes you believe the Mars Candy Company is underestimating the percentage. State the appropriate null and alternate hypothesis to test your claim. Okay, so the null hypothesis. First off, we should note that we're talking about a percentage here, and usually the percentages is also can be considered a proportion. So we usually denote that by p, the proportion p, and the company states that it's 13%. 13% for a full size package should be plain M&Ms, brown plain M&Ms. Okay, so however, based on your observation there, 15% of the package for that sample you got, you feel that they're underestimating the number, and so the percentage, or you feel it's being underestimated, so it has to be greater than 13%. Once again, oftentimes we don't write that as a percentage. We often write it as 0.13 for either case there. Okay. All right, so that's how you formulate the null and alternate hypothesis. There's some claim in the statement, or asking you to run some type of test, and you break up that claim into a null and alternate hypothesis. Okay, so if you notice in this 3 examples, each one had a different inequality symbol. We had a less than symbol, a not equal symbol, and a greater than symbol. Well, that's important when you conduct a test, because that's going to tell you what type of test to run. And so the alternate hypothesis tells us that what type of test we're going to run, and the 3 types of tests there are is very similar to what we had earlier. Is we have a right tail test, which is corresponds to that we have a right tail alternate hypothesis. In other words, there's a greater than symbol in the alternate hypothesis statement. So we use this type of test when we are interested in detecting an increase. And then we have a left tail test. And the alternate hypothesis will involve a less than symbol. You use this when you're interested in detecting a decrease. And then a two-tail test. And that will involve a not equal symbol in the alternate hypothesis. And this is used when we're trying to detect any difference, whether it be an increase or a decrease. All right, so in this particular example here, this here is telling us we have a left tail test. So this first example there, we have a left tail test. And the second test here, or the second hypothesis, the second example, the alternate hypothesis tells us that we're conducting a two-tail test. And the third example here is telling us we are conducting a right tail test. Okay, so those are the 3 types of tests. Now, once you formulate this null and alternative hypothesis, it's usually the time to go collect data and calculate some numbers after you collect the data. And to do that, those calculations are what we refer to as a test statistic and a p-value. Okay. So to make a decision about whether to reject or fail to reject the null hypothesis, we need to compute what's called a test statistic and a corresponding p-value. So a test statistic, let me switch colors here. So a test statistic is a score that is based on a statistic from a random sample that corresponds to a parameter in the null hypothesis. We use it to determine how unusual or usual the statistic observed is, assuming that the null hypothesis is true. So we use it to determine how unusual or usual this test statistic that we observe from the sample data, right, assuming that the null hypothesis is true. The test statistic is used to calculate the p-value. which is the probability of obtaining a value as extreme or more extreme than the observed test statistic, assuming the null hypothesis is true. Okay, so we'll learn several test statistics in this course and learn how to calculate your p-values. Okay, and so that to talk about a couple of these test statistics, here's some examples. When we're performing a certain type of test, we're going to run into what's called a one-sample z-test, or just z-test for short. And basically, what this test is doing is just measuring how unlikely or likely it is to observe the test statistic that we obtained. Okay, and remember, the score here, the test statistic, is nothing more than basically observing some statistic, so some observation from that was based on some random sample, and you're seeing, how far this value deviates from the expected, what you would expect. Okay, what you would expect, so expected value. And then you would divide this by what's called the standard error. Okay, so so think like standard deviation. All right, standard error. And that's all these test statistics are. It's going to, for us, it will be a Z or a T. Of course, there are others. But for now, it's going to be like a Z score, as you've learned, and a T score, which is a T for the student T distribution, and Z for the standard normal distribution. Okay, so the first one here, for a one-sample z-test, we would use a z-score. In this case, this one is for a mean, and so you would have the sample mean, x bar, and you would subtract off the population mean, mu, and divide by the standard error, which is the population standard deviation, divided by the square root of n. Okay, so once again, this is z equals x bar minus mu, divided by the standard deviation, divided by the square root of n, where x bar is the sample mean, mu is the population mean, and sigma is the population standard deviation, and n is the sample size. Okay, so that's the test statistic that you would use for a one-sample z-test. The next one is also considered a z-test, but this time it's for a proportion, and the test statistic is z equal to p hat, which is the sample proportion, minus the population proportion, all over the square root of p times q over n. Okay, once again, the z test statistic is p hat minus p over the square root of q over n, where p is the population proportion of success, q is the population proportion of failures, and n is the sample size. Looks like I forgot to mention p hat is the sample proportion, which if you recall, sample proportion equals whatever the number of successes are divided by the sample size or the number of trials. Okay, and that's how you would run or crunch a test statistic for a one-sample z-test. All right, another type of test that we'll run is what's called a one-sample student's t-test. Okay, or just t-test for short. And this has to do with a test involving a population mean, and z, it's not a z no more, excuse me, it's a t-score now, and it's similar to the first one we just introduced, and x bar minus the population mean divided by, instead of the population standard deviation, it's going to be the sample standard deviation divided by the square root of n. And that is the test statistic, right? Once again, x bar minus the population mean divided by the sample standard deviation over the square root of n, where x bar is sample mean, mu is the population mean, s is the sample standard deviation, and n is a sample size. Okay, once again, these are the test statistics used to run a hypothesis test involving either a mean or a proportion. Okay, so let's do a calculations to see how we come up with these test statistics. So suppose we have the following hypothesis for a t-test for a mean. Okay, and once again, they come in pairs, right? So the null hypothesis is the claim that mu, or the population mean, is equal to 52.19. The alternate hypothesis is not equal to 52.19. So a random sample consisting of 23 individuals which resulted in a mean of 51.1 and a standard deviation of 1.62. Calculate the test statistic t-test for a mean. Okay, so round to 2 decimal places. All right, so first let's observe. We're going to be using t equals x bar minus the mean over s divided by the square root of n. Okay, so we need to identify what x bar is, the sample mean. Well, first let's identify the sample size. So what's the sample size? The sample size, we have 23 individuals. We also know that it was a sample, so we took a sample mean and got 51.1. And we got a sample standard deviation S of 1.62. And we know from the null hypothesis that the population mean, the claim valued in the null hypothesis, is equal to 52.19. Okay, so we put those numbers in to our formula. I'm doing it backwards here, so it's 51.1 minus 52.19, and then we divide that by 1.62 all over the square root of 23. Now we need to take a calculator, and I'm going to go ahead and use say Desmos. Here's Desmos. All right, so the t-score or test statistic here is a fraction, right? So we have 51.1 minus 52.19, and then we're dividing by the fraction 1.62 all over the square root of 23. Okay, and so we see we get negative 3.226824914. And so let's go back to the notes. T-scores or test statistics often are rounded to say 2 decimal places, so we get negative 3.23 as the test statistic. And what is the meaning of this? Well, the meaning is essentially that it's if you recall what a z-score is, well, a t-score is exactly the same kind of idea, right? You're standardizing the score and figuring out how many standard deviations your observation is above or below the mean. So in this case, we would say that, for instance, our observation of 51.1 is about negative 3.23 standard deviations below the expected value or the mean of 52.19, assuming that the null hypothesis is true. Okay, and so when we calculate a p-value, we want to know how extreme is that number, assuming that the null hypothesis is true. All right, let's move on to the next example here. All right, suppose we have the following hypothesis for a z-test for a proportion. The null hypothesis is p equal to 0.42. The alternate hypothesis is p greater than 0.42. A random sample consisting of 148 individuals with 63 successes. Calculate the test statistic z and round to 2 decimal places. All right, so once again, the test statistic we're using from what I mentioned above is p hat minus p divided by the square root of pq over n. All right, so let's identify our statistics that we need. Right, we need n, which was 148 individuals or trials, and the number of successes. I like to denote the number of successes using r, but some people use x. It doesn't really matter. R equals 63 successes, and that will give us our p hat, which is r over n, or 63 over 148. That's our number of successes, or sample proportion of successes. And then p, which is what's claimed in the null hypothesis, is 0.42. Okay, and we also need q, which is so p is the proportion of successes in the population, right? Q is a probability or proportion of failures in the population. So we would go 1 minus 0.42, and so that gives us oops, I put 0.48 there for some reason, 0.42. That gives us Q equal to 0.58. 148. Okay, and so now we can plug those numbers into our formula. So p hat would be 63 over 148. Then subtract off p, which is 0.42. Divide that by the square root of 0.42 times 0.58. And then divide that by n, which is 148. Okay, so now that we have the numbers plugged in, we could go ahead and take a calculator. I'm going to go ahead back and use decimals and punch this stuff in. All right, so our z test statistic here consists of a fraction, but our first entry p hat is a fraction, so I'm going to have the fraction bar again. We have 63 over 148 minus 0.42 divided by the square root of another fraction, where we have 0.42 times 0.58, all over 148. All right, so we see we get a test statistic of 0.1375, yada yada, which we will approximate to 3 decimal places. So let's go back to the notes and do that. So this will be, 2 different places. We'll approximate this to about 0.14. Okay, so what does this mean here? This means our observation of 63 over 148 is about 0.4 standard deviations above the mean, and I'm saying mean here, but above the proportion here of 0.42. Assuming the null hypothesis is true. So based on all just test statistics, this is not too far away from the p, and so we'll probably get a large p value if we would compute the p value for that. But in any case, that's how you compute the test statistics. All right, let's talk about the p-value. So the p-value is the probability under the assumption that the null hypothesis is true, that the test statistic takes on a value as extreme as or more extreme than the value observed. To calculate a p-value, you definitely have to use some kind of table or technology, because you're finding area under a probability distribution, a continuous probability distribution. In our case, the 2 continuous probability distributions that in this section or this topic we call sampling distributions will be using is the standard normal distribution or the student's t-distribution. Okay, and it depends on the type of test that you're conducting. So if you're conducting a left-tail test, that means typically your test statistic is going to be negative, and the p-value is going to be to the left of it. And the way, if this is the standard normal distribution, then the p-value, it's what's called a conditional probability. It's the probability that z is less than the test stat given that the null hypothesis is true. And so if this is the standard normal distribution and you use, say, Excel, for instance, the way you would find that p-value would be just norm.dis, the test statistic, 0 and 1 for the standard normal distribution, and then the last result there, a 1, just means true, and that will return the p-value to you. Now, if it's the student t-distribution, okay, the student t-distribution, which kind of has a similar shape than the normal distribution, it's also a conditional probability, but instead of using norm.dis, you use t.dis, and you input the test statistic and degrees of freedom, comma 1, and degrees of freedom for this particular type of test will be n-1. All right, so that was assuming it was a left-tail test. Now, if it were a right-tail test, that means our test statistic is typically positive, and that the area that we're looking for is to the right. Okay, so if it's the standard normal distribution, that would be, you would type in a cell, empty cell, 1 minus norm.dis, whatever the test stat is, 0, 1, 1. Now, if it were the t-distribution, then you would type in 1 minus t.dis, the test stat, the degrees of freedom, and 1. Okay, once again, please note it's a conditional probability, right? The p-value is a conditional probability. In this case, z or t is greater than test stat, such that the null hypothesis is true. Not such that, but given that the null hypothesis is true. All right, and then the last case, or last type of test is a two-tailed test, and this one is has 2 cases. because the test stat could either be negative or positive. And so if it's negative, then what you have is this test stat over here, and the p-value is split into the two tails. Okay, so if this were the standard normal distribution, the way you find the p-value is essentially to go 2 times norm.dist test stat 0, 1, 1. Okay, and that would give you half of the area, but doubling it gives you both tails. Okay, and if it was the student t test, student t distribution, then you would use t.dist. This time you would double it, test stat, degrees of freedom, and 1. All right, but if the test stat were positive, that means it's over here. And so we would do something similar. If it was the standard normal distribution, we're going to double first find the area in the right tail and then double it. So to find the area in the right tail there, that's just 1 minus norm.dist, test stat 0, 1, 1, and then we double it. If it were the student t distribution, we once again find the area to the right of the test statistic, which is 1 minus t.dist, test stat, degrees of freedom 1, and then you double it to get the both tails. All right, so that's how you find the p-value in those two specific situations, or the 3 different tests, and not only that, depending on the type of test statistic you're using as well. Okay, so moving on, let's see some examples here. All right, so the first example, you're conducting a 1-sample z-test for a mean. The null hypothesis is h0 mu equals 54.3, and the alternate hypothesis is h1 mu equal to not equal to 52. Actually, I made a mistake here. Let's change this here and actually make that a less than. Okay, and so the alternate hypothesis h1 is mu less than 54.3. Your sample consists of 22 individuals with a mean of 53.3 and a population standard deviation of 2.18. The sample test statistic z, rounded to the hundredths place, is negative 2.15. Find the p-value and shade the area under the sample distribution corresponding to the p-value. All right, let me just quickly note here. So h0 is the mu equal to 54.3. That's what we're assuming to be true, right? And then the mean is less than 54.3 is the alternate hypothesis. So this tells us it's a left tail test. Okay, and that's important when we find the p-value. So the test statistic is given to us. We could compute it by using the formula x bar minus mu divided by sigma divided by the square root of n, but they told us it's equal to negative 2.15. Okay, so we're using a z-test because it's the standard normal distribution here, and under that peak there's it's 0, and negative 2.15 is about right there, and the p-value would be to the left there, and so that's the p-value that we're interested in. All right, so the p-value can be found using Excel's. Go here. The p-value can be found by going into an empty cell and typing in equals norm.dist and then a negative 2.15, 0, 1, 1, close parenthesis. Okay, so let's show you how to do this in Excel. So here's Excel. Let's go ahead and increase the font here, or zoom in just a tad. So here in cell A1, I'm going to type a equals, and I'm going to go norm.dist, type in my negative 2.15 for the test statistic, 0 for the mean because it's the standard normal distribution, and 1 for the standard deviation as well because it's the standard normal distribution, and then a 1 for true or whatever number other than 0 there, and you would get 0.015776, so forth. Okay, so go back to the notes. Typically, p-values are rounded to about maybe 4 decimal places, so 0.0158 would be our p-value. Okay, so let's go ahead and look at another example here. You are conducting a 1-sample t-test for a mean. The null hypothesis, H0. h sub 0 or h naught is the mean equals 15.1, and the alternate hypothesis is the mean is greater than 15.1. Your sample consists of 15 observations with a mean of 16.2 and a standard deviation of 3.04. The sample test statistic t rounded to the hundredths place is 2.44. Find the p-value and shade the area under the sampling distribution corresponding to the p-value. All right, so let's take note of the null hypothesis. We know the null hypothesis is mu equal to 15.1. The alternate hypothesis is mu is greater than 15.1. And in order to calculate this p-value, we would have to first calculate test statistic, but they give it to us, and that is equal to x bar minus mu divided by sigma over the square root of n. Okay, and so they tell us that number is 3.04. All right, so this is the student t. The student t also has a mean of 0 under the peak there, and 3.04 would be over here in the tail, and we're looking for that number there. That's the p-value. Okay, in order to calculate the p-value, we need to calculate the degrees of freedom, which is n minus 1. All right, but we're told that n minus 1, or excuse me, the sample size, this was based off 15 observations, so 15 minus 1 is equal to 14. Okay, so then the area is to the right, so because it's a right tail test, right? Right tail test. Okay, as we can see from the picture. But the p-value then can be found by going equal into an empty cell, in Excel for instance, or using a t-table or something. But p-value, I'm going to show you how to use Excel. We would go 1 minus t.dis, and then our test statistic of 3.04, comma, the degrees of freedom, which in this case is 14, and then I like to use 1 for true. All right, so let's go to Excel and calculate that. All right, so here's an empty cell, and get rid of that one. We don't need it no more. And so we have equals 1 minus t.dis, and then 3.04, 14 for the degrees of freedom, and then 1 for true. And so that there is our p-value. Okay, let's go back to notes. Let's round this value to 4 decimal places. So we get 0.0044. That's the p-value. All right, let's try one more example here that calculates the p-value. So you are conducting a one sample z-test for a proportion. The null hypothesis is h0 equal to, where h0 is the proportion equals to, p equals 0.30, and the alternate hypothesis is p is not equal to 0.30. So your sample consisted of 225 trials, 88 successes, which gave a sample proportion of 0.39. The sample test statistic z rounded to the hundredths place is 2.95. Find the p-value and shade the area under the sampling distribution corresponding to the p-value. All right, so the null hypothesis is p equal to 0.30. The alternate hypothesis is p not equal to 0.30. All right, so we have to calculate a z-score, or z-test statistic, and we know this one is p hat minus p divided by the square root of pq over n. Now, they gave us this value, so we don't have to do the number crunching. They told us that we had a test statistic of 2.95, but we need to shade this area, and the way we're going to shade this is by first examining the alternate hypothesis, because that tells us it's a two-tailed test. Okay, and so since it's a two-tailed test, that means our test statistic of 2.95 is somewhere right here. Okay, but then the corresponding other one is over here, which would be the negative of that, and the p-value, half the p-value is to the right of it, and half to the p-value, and the other half is to the over there on the other end. Okay, so that's half the p-value. Half the p-value on both sides. And so you're going to see me double something up right now. All right, so then the p-value, and this is a z-test statistic, that means we're using the standard normal distribution, can be found by going equals twice the area to the right of 2.95. So to do that, we would go parenthesis 1 minus norm dot dis, and clean that up just a tad there, comma, open parenthesis, then our test statistic of 2.95, comma 0, comma 1, comma 1, close the parenthesis, and then close the outer parenthesis. All right, there. Let's go to Excel to do that calculation. All right, let's get rid of this here. We don't need it. So we're going to go equals 2 times open parenthesis 1 minus norm dot dis 2.95, comma 0, comma 1, comma 1. Close that parenthesis. Close the other one. That should be it. All right, so we got a p-value of 0.003177. Okay, so let's round that to, let's go back to the notes and round that to 4 decimal places. So this is roughly going to be 0.0032. All right, so that's how you find a p-value. The next concept here is how to conclude a statistical test once you've found the p-value. All right, so when conducting a hypothesis test, the p-value is compared to what's called a significance level, alpha. More said about that later. If the p-value is less than or equal to alpha, you reject the null hypothesis, which typically means the data are statistically significant. If the p-value is greater than alpha, then you fail to reject the null hypothesis. Okay, a hypothesis test is designed to test a claim, and this claim is often the statement of the alternate hypothesis, but it can be the statement of the null hypothesis. The following flowchart can be used to guide you on how to state the result of the hypothesis test. All right, so quickly here, go over this flowchart here. So if the claim is the null hypothesis, which is usually not the case, but it can be, you tend to, if you reject the null hypothesis, so that means yes, we would follow that up to yes. So wait, the claim is the null hypothesis, and we reject the null hypothesis, so that's yes. We would state something like, there is enough evidence to reject the claim that ... Okay, we might also say that at the significance level alpha equal to 0.01, there's enough evidence to reject the claim that ... All right, but if we don't reject the null hypothesis, we might say at the alpha level of significance, there is not enough evidence to reject the claim, okay, or reject the null hypothesis. All right, but the use of cases when people run hypothesis tests, usually the claim is the alternate hypothesis, and so this is how you would state something. So if the claim is the alternate hypothesis and you reject the null hypothesis, that means there's enough evidence to support the claim that ... Otherwise, if you did not reject the null hypothesis and concluded no there is not enough evidence to support the claim that ... All right, let's see maybe an example of how we can do that. Go back to this example here. So boxes of a certain kind of cereal are labeled as containing 20 ounces. An inspector thinks that the mean weight may be less than this. So to test her claim, she performs a test of a null hypothesis, the mean is equal to 20 versus the alternate hypothesis, mu less than 20 at a significance level of 0.05. The p-value is 0.0173. How does the inspector conclude the test? State the appropriate conclusion. So once again, we first examine the p-value. The p-value is equal to 0.0173. And this here is less than our significance level of alpha of 0.05. Okay, and so what does that mean? That implies we're going to reject H0 and essentially accept H0 or support it, the alternate hypothesis. So the claim is the alternate hypothesis, so we're going to reject. Did we reject the null hypothesis? Yes. Okay, so that means there is enough evidence to support the claim that the cereal. So let me write a quick statement here. So we might say something like this: at 0.05 level of significance. This could be stated differently as well. There is enough evidence to support the claim, right? And what is the claim? That the mean weight of this certain cereal is less than 20 ounces. Okay. Let's look at another example here. So the Mars Candy Company claims the percentage of brown M&Ms is 13% for a full-size package of plain M&Ms. To test the company's claim, you perform a test of the null hypothesis P equal to 0.13 versus a alternate hypothesis P not equal to 0.13 at a significance level of 0.05. The p-value is 0.0725. How do you conclude the test? State the appropriate conclusion. All right, so we can see that the p-value, right, is equal to 0.0725, and this is actually greater than 0.05, which is your significance level alpha. So what does that imply? Well, that implies we are going to fail to reject the null hypothesis. All right, so what can we state? We might state something like the following here. At alpha equal to 0.05 significance level, there is not enough evidence to reject the null hypothesis, the null hypothesis, which is what? To reject that brown M&Ms make up 13% of a full size package of plain M&Ms, but I'll just cut it off there. All right, so that's how you conclude it. You compare the p-value with the significance level, and based on that comparison, you either reject or do not reject the null hypothesis, and you need to conclude it. And I like to say, explain it in a way that maybe someone at the bus steeple will understand. All right. Next concept here is type 1 and type 2 errors and level of significance. So a hypothesis test is like a criminal trial. At the start of the trial, the defendant is assumed to be innocent, which we think of as the null hypothesis. Then evidence is presented to the jury. Okay. If the evidence is strong enough to indicate that the defendant is guilty, then the jury abandons the assumption of innocence and finds the defendant guilty, which is the alternate hypothesis. However, if the evidence is not strong enough to indicate the defendant is guilty, then the jury does not abandon the assumption and the defendant is innocent, which is the null hypothesis. So think you're assumed to be innocent until proven guilty, right? That's the slang or the slogan that goes with that. Okay, so here in this example, we're asked to determine when a criminal trial works as expected and when it doesn't. All right, so here to do this or to understand this type of what I'm trying to introduce here is something called type 1 and type 2 errors. Let's use this example to help us understand that. All right, so what we have here is the table, and suppose we have a person who is on trial. So we assume that they are innocent. That's the assumption. And then we're going to present evidence to the jury, and that they would decide if to fail to reject that assumption if he's innocent or she's innocent, and conclude that they're guilty or not guilty. Okay, so that a jury decides that, right? And so this means the jury decides the defendant is guilty and not guilty, and then there's the reality. This is what we never really know, right? Only some higher being like God or something will know the reality. Okay, so they're really innocent or really guilty. All right, so if the jury makes a decision that the defendant is guilty and they're really innocent, well, is that a good thing or a bad thing? That is unfortunately a bad thing, right? That's bad. or not good, I should say. That's bad, and I'll just say bad there. All right. But if the jury decides they're guilty and they're really guilty, well, that actually is good. That's actually a good thing, right? Okay, but if the jury decides that they are not guilty and they are really innocent, well, that's a good thing. That's good. Okay, if the jury decides that they are not guilty and they are really guilty, that is a bad thing. I like to joke and say that's the O.J. Simpson case. Okay, but in any case, so we have bad and good, right? So when the test didn't work, right? In other words, the criminal trial, the justice system, didn't work. That's, how do you say? That's what we call error, right? Error. And if, on the good part, that's the correct decision. That's what should happen. In other words, it worked, right? And it worked. Okay, so what I'm trying to introduce here is something called type 1 and type 2 errors. So definition, rejecting a true null hypothesis is called a type 1 error, and failing to reject a false null hypothesis is called a type 2 error. And so what we see here is the same pretty much table. The decision, right, from the test, the hypothesis test, is either going to reject the null or fail to reject the null. And the reality is, we never know the null hypothesis is true or the null hypothesis is false. That's the reality, right? Only God or some super higher being knows the reality. Okay, so set up exactly the same in the table above. And so in the first case, this was this first cell, right? If the decision of the test came out to reject the null, but the null hypothesis is true, well, that's error. And that's what we call a type 1 error. And type 1 error. If the test came out to reject the null and the null hypothesis is false, well, that's a correct decision. And then if the test was concluded to fail to reject the null hypothesis and the null hypothesis is actually true, well, that's good. That's the correct decision. And if the null hypothesis or the hypothesis test concluded that it was to fail to reject the null, right? Do not reject the null. But the reality is that the null hypothesis is false. That's bad, right? That's error, and that's the type 2 error. Okay, so the significance level, what the significance level is, right? And we usually denote it as alpha. It represents the probability of making a type 1 error. So in other words, making a type 1 error, alpha. That's alpha there. Okay, the probability of making a type 2 error, the probability of making a type 2 error is usually denoted as beta, and that's that could be right there. All right, and the probability of making a correct decision is 1 minus beta, and the probability of making a correct decision in this cell is 1 minus alpha. Usually this here is referred to as the power of a test, and 1 minus alpha, we've seen that before, that's the confidence level. I'm not going to say too much except the following. Error is bad in general. If you go into maybe an intermediate statistics class, you will discuss these issues in great detail. But alpha and beta are both bad, right? I mean, and then there's type 1 error and type 2 errors are both bad. You want to minimize, both. But unfortunately, what happens typically is that as you try to decrease a type 1 error, alpha, you get an increase in a type 2 error in beta, and vice versa. And so sometimes it's helpful to, when you're setting these when you're setting your significance level to run a hypothesis test, you want to probably take note and think about the ramifications of making a type 1 error and a type 2 error. Let's go ahead and try this exercise here. The dean of a university wants to determine whether the mean salary of graduates of her school is greater than $50,000. She performs a hypothesis test with the following null hypothesis. The mean is equal to $50,000, so that's the null hypothesis. The alternate hypothesis is the mean, right? The average salary or the mean salary of graduates is greater than $50,000. So that's the test, right? That's the pair. Okay. Suppose this is the outcome. Suppose that the true mean, or the reality, so this is the reality that we never know, is $50,000, and the dean rejects the null hypothesis. Is this a type 1 error, a type 2 error, or a correct decision? Well, this is what we call a type 1 error, right? Since the dean rejected a true null hypothesis. All right, so part B here, suppose that the true mean is $55,000, right? This is the reality that we never know, and the dean rejects the null hypothesis. Is this a type 1 error, a type 2 error, or a correct decision? Well, this is bad. This is not bad, excuse me. This is the correct decision because the mean in the null hypothesis is $50,000, but the reality is that it's actually $55,000. So this is rejected, and that's the correct conclusion, that it's greater than $50,000. And so that's the correct decision. Since H0 is false. Now keep in mind, we really don't know this. We take it on faith that our hypothesis test concludes correctly, right? But we are aware of these type 1 and type 2 errors. Next one here. The reality, or the true mean, is $55,000. And the dean does not reject the null. This is a type 1 error, type 2 error, or correct decision. Well, this is a type 2 error. The reason is the reality is 55,000. So that means the null hypothesis, this is false. And we did not reject it. Okay. And so, this is a type 2 error. And so, since the null is false, but not rejected. Okay, so once again, these are just some examples of how to understand type 1 and type 2 errors. In reality, you don't know if you're making a type 1 error or type 2 error because you're conducting a test to help us decide an outcome. And we don't know the reality, but we're using the test to help us determine a conclusion about that null hypothesis, to reject it or fail to reject it. All right, the last thing I want to touch on quickly here, basically what I've discussed in this video is how a statistical test, a hypothesis test, and pretty much broke it down into what's called 5 basic components. So once again, the null hypothesis, the alternate hypothesis, and a pre-low significance level. So the idea is that the evidence of the sample data is against the null hypothesis strong enough, we reject the null and adopt the alternate hypothesis. The level of significance alpha. Didn't copy correctly. Alpha is the probability of rejecting the null hypothesis when it's in fact true. Okay. The test statistic and sampling distribution, these are the mathematical tools used to measure compatibility of sample data and the null hypothesis, right? We compute the test statistic and based on the sampling distribution we're using. So if it was a z-test, then we were using the standard normal distribution, and that's how we decided the test statistic. The p-value, to find the p-value, you use that sampling distribution. So this is the probability of attaining a statistical test from a sampling distribution that is as extreme as or more extreme as specified by the H1. Then the sample test statistic computed from the data under the assumption that the null is true. Okay. The conclusion, right? The way you conclude a test is you compare the significance level and the p-value. So if the p-value is less than or equal to alpha, we reject the null hypothesis and say the data are significant at level alpha. Sorry for my math notation didn't render. If p-value is greater than or equal to alpha, in fact this should be just simply greater than alpha, we do not reject the null. And then finally, you interpret the context, interpret the results of the test, giving a simple explanation of your conclusions in the context of the application, so someone at the bus depot will understand you. All right, so that's my quick little, that's my introduction to statistical tests.